Okay, I think we are discussing about the determination of structure. Okay, more particularly the aldotrioses, aldotetroses, and aldopentoses. So here I'm taking aldopentoses, and you can observe that there are five carbon atom in it. Let's give an entry. Okay, there are five carbon atoms, and how many chiral carbon atoms are present? So there are three chiral carbon atoms are present. This star indicates chiral carbon atom. So since three chiral carbon atoms are present, if you want to find out the number of isomers possible with the three chiral carbon atom, you can write 2 to the power of n. Here n is equal to number of chiral carbon atom and 2 to the power of 3. So that can be written as a 2 into 2 into 2. That means 2 fours are 2 twos are 4, 4 twos are 8. So that means 8 optically active isomers are possible. And all 8 isomers are known as these compounds corresponds to the D and L isomers of ribose, arabinose, xylose, and lixose. So let's go to the next slide. In the next slide, I'm taking a tetrose and I'm converting the tetrose into pentose by using Kiliyani-Fischer synthesis. So you know that tetrose means two things, two types of compounds are available. One is erythro, another one is trio. Okay. In pentoses, four types of compounds are available: ribose, arabinose, xylose, and lixose. So now let's take the tetrose and let's convert a tetrose into pentose. Let's go to the next slide. So look here, erythrose I am taking. Erythrose is a aldopentoses. So when it is subjected to Kiliyani-Fischer synthesis, let's give an entry. Okay. Right. So when erythrose is treated with Kiliyani-Fischer synthesis, this CHO is converted into OH. Okay. So this CHO is converted into OH. A new aldehyde group is introduced by the Kiliyani synthesis. Anyway, I will explain what is Kiliyani synthesis maybe at the end of the today's class. So here what you can remember, when erythrose is subjected to Kiliyani synthesis, if the hydroxy group is going towards the right hand side, then it's called ribose. If this hydroxy group is going towards the left hand side, so this is the left hand side one, then it's called arabinose. That's only the difference between the erythrose and arabinose and ribose. So that means this part OH, OH, CH2 part is same in ribose as well as the arabinose. You can observe that. See OH, 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 and here OH, 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 OH. So only the difference on this carbon atom. Okay, that means this carbon atom. This carbon atom, if the OH is on the right hand side, then it is ribose. If the OH is on the left hand side, then it is arabinose. Okay, and how this CHO is converted into OH by doing Kiliyani-Fischer synthesis. What is Kiliyani-Fischer synthesis? It is treated with hydrogen cyanide. So hydrogen cyanide will add it to CHO, OH, oxygen form a bond with the hydrogen, CN form a bond with this carbon, giving rise to nitrile. So nitrile is hydrolyzed. That is, hydrolyzed means nitrile is converted into carboxylic acid, and then this CH2OH. That's all. And then reduced. Okay, carboxylic acid is reduced to CHO. This CHO is newly formed aldehyde, and this CHO is converted into OH. Okay, in arabinose, OH is on the right hand side. In ribose is on the right hand side. Arabinose, OH is on the right hand side. That's what you need to remember when we are taking erythrose. Suppose if we are taking 3-Os, then these two, this hydroxy is on the left hand side. That's all the difference. Remaining thing continues. But anyway, that I will explain in the next slide. Once you got ribose as well as arabinose, so both the compounds are subjected to oxidation. So oxidation means treating with nitric acid, HNO2, HNO3. HNO2 is nitrous, HNO3 is nitric. So what is happening here? An aldehyde, CHO, is converted into carboxylic acid. Similarly, this primary alcohol is also converted into carboxylic acid. That means a diacid is obtained. More particularly, what you can observe, so there is a plane polarized light passing through this carbon atom. Since this moiety contains a plane polarized light, then the compound is optically inactive. Then a arabinose, when it is subjected to oxidation, more particularly nitric acid oxidation, it gives optically active. So why? Because it does not contain a plane polarized light. So that is the reason it is optically active. So what it means? D-erythrose, when it is subjected to Kiliyani-Fischer synthesis, it gives D-ribose and D-arabinose. The obtained D-ribose and D-arabinose subjected to oxidation gives rise to diacids. One is optically inactive, another one is optically active compound. So with this, I will go to the next slide. Next slide, I'm taking what you call 3-Os. 3-Os means priority group. OH groups are on the opposite side. So I am taking 3-Os. 3-Os is also a aldotetrose. This aldotetrose is converted into aldopentose by employing a Kiliyani-Fischer synthesis. So Kiliyani-Fischer synthesis converts this CHO into OH. In one molecule is right hand side, in another molecule it's on the left hand side. The hydroxy is on the right hand side, one is called xylose. The hydroxy is on the left hand side, one is called lixose. And this CHO is newly introduced by employing a Kiliyani-Fischer synthesis. So the obtained xylose and lixose subjected to oxidation, giving rise to optically inactive carboxylic acid and optically active carboxylic acid. So optically inactive, that's because of the presence of plane polarized light passing through this carbon atom. And this moiety does not have a plane polarized light. That is the reason it is optically active. So this is about what is called as determination of structure of aldopentoses. So let's take the one more compound. What is that? Aldohexoses. So this is a aldohexoses. Aldo stands for aldehyde. Exos means X means uh, 6 carbon atom. OSC means it's a suffix for the carbohydrate. How many carbon atoms are there? 1, 2, 3, 4, 5, 6 carbon atoms are there. How many chiral carbon atoms are there? 1, 2, 3, 4. 4 chiral carbon atoms are there. Since it contains 4 chiral carbon atom, how many isomers are possible? Stereoisomers. That is 2 to the power of n. N is equal to number of chiral carbon atom. That is equal to 2 to the power of 4. That is equal to 2 into 2 into 2 into 2. That means 2 twos are 4, 4 twos are 8, 8 twos are 16. 16 optically isomers are possible. So all these 16 uh, active isomers are known, and these compounds are D and L isomers of D and L isomers of allose, maltose, halose, maltose, glucose, mannose, glucose, idose, galactose, and talose. So you need to remember. Why? Because they used to ask a question on Aldohexoses, or maybe a Aldopentoses, or maybe a Aldohexoses, or maybe a Aldotrioses. So give the structural determination of Aldohexoses, Aldopentoses, Aldotetroses, Aldotrioses. Then you should be able to write the answer. So with this, I will go to the next slide. In the next slide, I am taking aldopentoses. I am converting aldopentoses to the aldohexoses by employing Kiliyani-Fisher synthesis. I will go to the next slide. Here, I am taking D-ribose. So how will you get the D-ribose? D-ribose, it is possible to get starting with the conversion of a aldotetroses into aldopentoses. So I'm taking D-ribose, and you can observe that OH, 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 OH. So 4 OHs are there in the right hand side. In the product also, OH, 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 OH. 4 OH groups are in the right hand side in the halos. So in aldose also, 4 OH groups are in the right hand side. OH, 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 OH. So then what is the difference? So only the difference in the second carbon atom. So that means here ribose contains an aldehyde. No? That aldehyde group is converted into hydroxy group. How it is converted? By treating, by employing the Kiliyani-Fisher synthesis. So what is Kiliyani-Fisher synthesis? It is a nothing but a reaction of hydrogen cyanide followed by hydrolysis and then reduction is called Kiliyani-Fisher synthesis. In this process, whatever the aldehyde present in a ribose is converted into hydroxy group, and the new CHO group is introduced to the first position. It's called Kiliyani-Fischer synthesis. Suppose a hydroxy group is going towards the right hand side, then it is called halose. If the hydroxy group is going towards the left hand side, then it is called aldose. The obtained halose as well as aldose subjected to oxidation In this process, a CHO group is converted into carboxylic acid. A primary alcohol CH2OH is also converted into carboxylic acid and giving rise to two compounds. One is optically active carboxylic acid, another one is optically active carboxylic acid. So why it is optically inactive? Because of the presence of plane of symmetry. The plane of symmetry is passes between the these two carbon atoms. A plane of symmetry passes between these two carbon atoms and bisects the molecule into two equal halves. So that is the reason it is optically inactive. And this one is optically active because there is no plane of symmetry. Of course, it contains chiral carbon atoms. 1, 2, 3, 4. 4 chiral carbon atoms are present in this dicarboxylic acid. So this is about how the ribose is converted into D-halose and D-aldose and further converted into dicarboxylic acid. So in the next slide, I am taking one more pentose and I am converting another pentose into a hexoses. So here I am taking arabinose. So arabinose is also a pentose sugar and the arabinose subjected to Kiliyani-Fischer synthesis. When it is subjected to Kiliyani-Fischer synthesis, this already present aldehyde group is converted into OH group. And newly a aldehyde group is introduced to the first position. Suppose a hydroxy group is on the right hand side, then it is called glucose. If this hydroxy group is going on the left hand side, then it's called mannose. So that means D-arabinose is converted into D-glucose and D-mannose. The obtained D-glucose and D-mannose subjected to oxidation, giving rise to optically active compound. Name of this compound is also called as saccharic acid. And so in this one, both are optically active. The obtained dicarboxylic acids both are optically active compounds because there is no plane of symmetry. Here also there is no plane of symmetry. That is the reason both the compounds are optically active. So this is about how the arabinose is converted into D-glucose and D-mannose. In the next step, I am taking one more pentoses and I am converting the pentoses into hexoses by employing Kiliyani-Fischer synthesis. So look here, here I am taking D-xylose. This D-xylose subjected to Kiliyani-Fischer synthesis. The CHO group is converted into OH and new aldehyde group is introduced by employing a Kiliyani-Fischer synthesis. Suppose a hydroxy group is on the right hand side, then it is called gulose. If this hydroxy group is on the left hand side, then it is called iodose. The obtained glucose and iodose subjected to oxidation, giving rise to a dicarboxylic acid, and the obtained both the dicarboxylic acids are optically active because of the absence of planar symmetry. Is it clear? So, in the next slide, again, I am taking one more Aldo pentoses, that is called the Lixose, and I am converting the Lixose into Exoses. Okay, so this is the Lixose. This D-Lixose subjected to Kiliyani-Fischer synthesis. During Kiliyani-Fischer synthesis, the CHO group is already present, is converted into OH. In one molecule, right-hand side occupies. In another molecule, OH occupies on the left-hand side. And during Kiliyani synthesis, a CHO group is introduced to the first position. So this is the CHO, this is the CHO. Then what are the products obtained? The obtained one is D-galactose and D-talose. So that means D-lixose on reaction subjected to Kiliyani-Fischer synthesis, it gives D-galactose and D-talose. Both the exoses subjected to oxidation, so giving rise to optically active dicarboxylic acids. Obtained dicarboxylic acids does not have a plane of symmetry. That is the reason both are optically active. So up to this, we discussed about the determination of structure of carbohydrates. The carbohydrate may be a triose, or may be a tetrose, or may be a pentose, or may be a hexoses. Only two trioses are there, that is D-glyceraldehyde and L-glyceraldehyde. Using D-glyceraldehyde and L-glyceraldehyde, it is possible to convert a triose into tetrose. In the tetrose, two molecules is obtained. One is erythro, another one is threose. And using tetrose, it is possible to convert into a pentoses. Okay, 4 pentoses. It is possible to convert a tetrose into 4 pentoses. So using 4 pentoses, it is possible to convert into 8 hexoses. Okay, so this is about what is called as determination of structure of carbohydrates. I think in the case of Aldohexoses, so there are 8 compounds. So how to remember this 8 Aldohexoses? So for that, I am giving one memory method of writing Aldohexoses. So in order to write the Aldohexoses 8 compounds without mistake, so you need to follow certain rules. So that rules I am explaining in the next slide. So this is the one. If you want to write the 8 Aldohexoses, first you have to write the skeleton. This is the skeleton. In the first place, you write CHO. Next, you leave the blank. Second carbon atom, leave the blank. Third carbon atom, leave the blank. Fourth carbon atom, leave the blank. Fifth carbon atom, leave the blank. And the sixth carbon atom, you fill CH2OH. So like this, you write 8 times. Are you following? Hello?
Yes, sir.
What you can do, you write this structure first on a notebook. All of you write this skeleton on a notebook, more particularly a rough notebook. Write down, all of you write down this skeleton on a notebook. And more particularly, you have to write 8 times. So this is the one time I have written here, but you have to write 8 times. Written? Written?
Yes,
Right.
sir.
Okay. After writing 8 times of this skeleton, then what you can do? Fifth carbon atom. What is the fifth carbon atom? This one is the fifth carbon. You have to start numbering from the aldehyde. This is 1, 2, 3, 4, 5. So to the fifth carbon atom, right hand side, write OH 8 times. Find out the fifth carbon atom, write the OH to your right hand side, 8 times you write.
Yes, sir.
And then find out the fourth carbon atom. Fourth carbon atom. Fourth carbon atom means you start the numbering from the aldehyde. That is aldehyde is 1, next is second, and the next is third, and next is fourth one. So fourth one, no, OH right hand side 4 times and left hand side 4 times. First write OH right hand side at the fourth carbon atom 4 times. Next 4 you write on the left hand side.
Yes, sir.
Written? Next, find out the third carbon atom. Aldehyde is the first, second, and third. Third carbon atom, write 2 times OH right hand side and 2 times OH left hand side, and repeat that sequence. For the third carbon atom, OH write OH 2 times right hand side and then 2 times left hand side. Repeat this sequence until for the 8 molecules. Written?
Yes, sir. Yes, sir.
Then go to the second carbon atom. Write write down OH 1 time to the right and 1 time to the left, and repeat this sequence until you reach the 8th carbohydrate.
Yes, sir.
Okay. So now you need to give the names to the 8 compound. Okay. I will go to the next slide. I will show you. So look here. The first one is called halose. Second one is called aldose. Third one is called D-glucose. Fourth one is called D-mannose. Fifth one is called D-glucose. Sixth one is called D-iodose. Seventh one is called D-galactose. Eighth one is called D-talose. And here there is a leftover thing. What is leftover thing? So here empty is there, no?
Hydrogen atom.
Hydrogen, that you fill it automatically. So wherever there is no OH group, no, those positions you fill it with hydrogen. So this is about the configuration, determination of configuration of Aldohexoses. Is it clear? Is there any doubt?
No, sir.
Okay, so this is about Aldohexoses, and Aldopentoses you have to remember, there is no other choice. Aldotrioses you have to remember. Aldotrioses only two components, D-glyceraldehyde and L-glyceraldehyde. Aldotetroses it's only two compound, erythrose and threose. Erythrose means hydroxy, both the hydroxy groups are in the same side. Threose means hydroxy groups are in the opposite side. That is about tetrose. And regarding aldopentoses, four compounds is possible. Okay, two compounds with erythro you are getting, two compounds you are getting from the trio. Okay, so if you are familiar, you should be familiar how to write the aldotrioses, how to write aldotetroses, how to write aldopentoses, and aldohexoses. You can follow this method of remembering all the 8 carbohydrates. Clear, no?
Yes, sir.
So now I will explain about Kiliyani-Fischer synthesis. What is Kiliyani-Fischer synthesis? So in order to explain the Kiliyani-Fischer synthesis, first I will take a general aldehyde. So I will go to the next slide. So this is explained. So this is the one. Kiliyani-Fischer synthesis. There are questions on Kiliyani-Fischer synthesis. So describe Kiliyani-Fischer synthesis with an example. Usually this is for, this can be for 2 marks question or maybe a 5 marks question. So for the 2 marks question and 5 marks question, you need to differentiate. So here what is I am taking? I am taking an aldehyde. An aldehyde, it is treated with hydrogen cyanide. So what is happening? There is a addition reaction. Hydrogen, it will form a bond with the oxygen, and Cn minus, it will form a bond with the electron deficient carbonyl carbon. So here there are two possibilities. Suppose Cn is attacking from this side. Okay. Since this electron deficient carbonyl carbon is a planar one, and nucleophile Cn minus can attack from both the side. If it is attacking from this side, it will give you this isomer. And again, this center is called prochiral center. Why? Because once the nucleophile Cn minus is attacking this center, it gives a racemic mixture. Racemic mixture means it's a mixture of enantiomers. So these two are the enantiomers, and these two are the non-superimposable mirror images to each other. So that is the reason it is possible to get two products, and it is a addition reaction. And what is the name of this compound? Cyanohydrine. This group is called cyano and this is hydrine. Hydrine means OH. Of course, this is also a cyano, this is also a hydrine. Is it clear? Is there any doubt in this one? So this is only the addition of HCN to the carbonyl compounds. Is there any doubt here?
No, sir.
This is called addition reaction. HCN is added to carbonyl compound. Oxygen form a bond with hydrogen. CN form a bond with the electron deficient carbon. And here Cn minus can attack from both the sides, this side as well as this side. If it is attacking from this side, this isomer is formed. If Cn minus is attacking from this side, this isomer is formed. And in both the compounds, we will call it as a racemic mixture. So this is about how the cyanohydrine is formed. But cyanohydrine formation is different. Kiliyani-Fischer synthesis is different. Kiliyani-Fischer synthesis is different. Cyanohydrine formation is different. So cyanohydrine formation is only the one step of the Kiliyani-Fischer synthesis. So in the next slide, I am explaining with example how what is Kiliyani synthesis. So I will go to the next slide. So look here, what I am taking arabinose. I am taking arabinose as the example for the Kiliyani-Fischer synthesis. So what is the first step of Kiliyani-Fischer synthesis? Addition of HCN. HCN is added to the aldehyde group. As I mentioned previously, oxygen form a bond with the hydrogen and nitrile, it will form a bond with the electron deficient carbon. Okay, and here I am writing Cn at the top because it's most oxidized one. And this method of writing structure is called Fischer projection formula. Okay, so Fischer projection formula method of writing is used in carbohydrate. This method of writing only is called Fischer projection formula. The most oxidized part is written on the top of the molecule. So this is a most oxidized, this is also a most oxidized. And here cyanide, if it is attacking from this side, this isomer is obtained. If cyanide is attacking from this side, this isomer is obtained. Two enantiomers are possible when a Cn minus is attacking the arabinose. So what are the enantiomers? One is D-gluconitrile. Nitrile means Cn. Gluconitrile. Then D-manonitrile. Cn stands for nitrile. So that means these two are racemic mixture. Of course, these two are enantiomers. How these two are obtained? By the addition of Cn minus to the arabinose. And the obtained nitriles are subjected to hydrolysis. What is the hydrolyzing agent? Barium hydroxide. Just like sodium hydroxide, potassium hydroxide is there, no? Barium hydroxide is also a base. So barium hydroxide is used to hydrolyze nitrile into carboxylic acid. Similarly, manonitrile subjected to hydrolysis by using hydrolyzing agent called barium hydroxide. Barium hydroxide converts a nitrile into carboxylic acid, and this nitrogen will go out as a ammonia. It will go out. Of course, this nitrogen also will go out as a ammonia. Then what is the product obtained? A monocarboxylic acid. This is called D-glucanoic acid is obtained, and this is D-mannanoic acid is obtained. And then the obtained monocarboxylic acid is subjected to dehydration. I think you are aware that there is a difference between the dehydration and the dehydrogenation. So what is happening here? H2O is not removed, only it removes H2. H2 is removed, isn't it? So, what will happen? This carboxylic acid, otherwise what we can say that on heating followed by reduction. On heating, the obtained monocarboxylic acid on heating followed by reduction converts a carboxylic acid into aldehyde. The obtained one is called D-glucose. Similarly, D-mannanoic acid subjected to on warming followed by reduction converts a carboxylic acid into aldehyde, and the obtained compound is called D-mannose. So this complete step, complete step starting with arabinose to glucose and mannose is called Kiliyani-Fischer synthesis. So if you are writing completely all these steps, you will get 5 marks. Is it clear? Is there any doubt in Kiliyani-Fischer synthesis?
That is H2O
No,
in
sir.
H2O, sir.
It should be actually what we can say that the heating itself is not required. Only the obtained monocarboxylic acids subjected to reduction. During the reduction, a carboxylic acid is converted into aldehyde. That's enough. Heating, removal of H2O is not required. Is it clear? Maybe you can erase this heating, removal of H2O. Both the things you erase and let it be the sodium amalgam water. This sodium amalgam is a reducing agent. Sodium and amalgam supplies electrons, and that electrons reduces a carboxylic acid into aldehyde. Is it clear? Is there any doubt? Is there any doubt in Fischer-Kiliyani synthesis? And also, if there is a doubt in determination of structure of aldose, triose, tetrose, pentose, hexose, that also you can ask. Is there any doubt up to today's class, starting from carbohydrate? So because in the next class onwards, I am taking a different concept, more particularly stereochemical aspects I will discuss. Any doubt? Hello? Hello? Any doubt up to this?
No, sir.
Okay. Right. Maybe what I will do,